Welcome and thank you for joining us for today's webinar featuring Arben, Pitarka, Douglas Dodge, Stephen Magana-Zook, and Stanley Ruppert, all from the Lawrence Livermore National Lab. As always, today's webinar is being recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, please mute your microphones. I still see a few turn on there. If you need to ask a question, use the chat window or patiently wait to the end of the webinar to ask your questions and turn your microphones back on. The presentation today will be approximately 50 minutes in length with questions and answers following during the remaining time. Today we are fortunate to have 4 experts from LLNL with us representing groups from across the laboratory, including global security, computation, seismology, and the geophysical monitoring program. Arben, Doug, Steve, and Stanley will talk today. Will focus on seismic processing, the challenges big data presents, the technologies at LLNL to tackle these, and the science it enables in their talk on ground motion simulation, seismic imaging, large-scale time series processing, and big data technology for solving earth science problems. So Arben, the screen is yours.
All right, thank you, Lauren, for the introduction. So yeah, today we're very excited to introduce to everybody some of the work that we're doing that is related to nuclear explosion monitoring, but also relates to earthquake modeling and seismic hazard and all related phenomena. So this presentation is going to be done by 3 people. Actually, I'll be the first one introducing the ground motion simulation and some work on seismic imaging, and the other 2 will be focus more on time series processing and big data technology and the application. All right, so let's see this. Yeah, so these are the main topics that I'm going to try to introduce you in just a couple of minutes. So first is some work that we're doing to model explosion sources using hydrodynamic modeling of the source process, and also elastic wave propagation modeling using complex 3D structures. I'll talk a little bit about seismic imaging and earthquake ground motion simulations, and then the last part of the talk is going to be mainly seismic source monitoring using waveform correlation. One of the main activities that we have right now regarding the source physics is a source physics experiment that aims at recording data from shallow chemical explosions with different depth of burial and also yield. And the idea is to understand how the waves are generated from explosions and also how they are propagated. But mainly we're after understanding how the shear motion and compressive motion is generated during those explosions, because those are the main features that we are looking at and recording at long distances, and they are basically the significant portion of the signal that we're trying to understand in order to discriminate between explosions and sources and earthquakes. And so in order to do that, we first try to actually model near field data and then try to propagate those to regional or local distances or teleseismic distances, and make a connection between what is the source contribution and the wave propagation contribution to the types of waves that we're observing. So in this figure, I just show a little bit the layout of the network of the stations. There are several linear arrays, but also there is a small array that is basically used to understand the waves that are generated near the source. We use Geodynamics, which is a hydrodynamic code that is developed by colleagues here at Lawrence Livermore to actually model the shock waves and the physics of the source. And then we, using a coupling technique, we propagate the near field to far field using the wave propagation code that usually we use WPP and SW4. The SW4 is similar to WPP, but it's fourth order, and it's actually it's an open source, and you can get it from CIG. Here I show some the first page of the user guide. Generally, we use our computation facilities here because these are really large problems. They involve millions and billions of grid points and hours of computation and a large amount of data. So just to give you an example, for a general run for the source physics experiment, we use about 3,240 CPUs, and that the computation takes like 12 hours. For the WPP, we use 150 billion grid points, and again, the same CPU time, but the computation usually takes like 8 hours. This is just to give you an idea what that involves. Now, the most important part that I was trying to introduce is that the modeling source is a very complex problem. Of course, it starts with preparing a 3D model, preparing a source model. So that involves a lot of parameterizations that I'm not going to go through, but as you understand, it does involve also the physics of the rock. And then we simulate the ground motion at a small portion of the area around the source, and then we plug it into a fine difference grid where the input motion is given along the faces of this cube, and then we propagate it to further distances. What we discovered during this experiment, and that's very important, is that actually there is a lot of significant shear wave energy generated right at the source due to the damage and the sliding motion in the joints, and that energy is actually amplified as it goes through the structure. And here I show a computation using Geodynamics, which is physics-based modeling, and a empirical model, which is a kind of isotropic source. And as you can see in the snapshot, the waveforms of the vertical motion are kind of, they start being some kind of symmetric, but then due to the structure, you do see a lot of curve. Here's the curve that just propagate through the structure. And if you compare waveforms, here I have a comparison between the recorded data, black, and simulated data, red, with a Miller-Murphy in this case, and in this case with a physics-based modeling, which does include the Geodynamics. And as you can see, we start seeing phases that look like what it is observed, and we start understanding what kind of shear waves are generated and how the surface motion is propagated to longer distances. Now, I'm going to switch to another case where we are trying to use our Bayes-Lock program, which uses a Bayesian location methodology to actually accurately locate micro earthquakes. And this is very important for several reasons. And micro Bayes-Lock is really well designed to make a joint location of the microsystem, so you can get a better location, but also it comes up with an error estimate, which is shown here for the case of Newbury seismicity. Of course, when you talk about location of seismic sources, you need also to have a very accurate velocity model. So in a connection with Bayes-Lock, we're doing a lot of research to come up with techniques that produce accurate underground structure. And one of them is the ambient noise correlation technique that one of our colleagues are working intensively. Here I'll show an example of different slices at different depths, and you can tell that how much detail you can see through the tomographic model that we get from the ambient noise. And here also on the left side, I compare the 1D Green's functions, which is a green line with the recorded data, and the 3D Green's functions with recorded data again, and you can see that there is a lot of improvement in that direction. And so by improving the structure, we can also do a much better reading of the P and S wave onset on the recorded data, because you can compare with a synthetic Green's function, and that turns into a better information for the base log code. And so they kind of feed each other, and you get a better location of the seismicity. And we're working on different projects, including oil exploration projects, to better understand the seismicity, the migration, and the mechanism of the earthquakes that are generated as a result of induced seismicity. Another interest that we have is in several regions of the world, we need to know better the seismic sources there, discriminate them, but that requires, of course, a good knowledge of the wave propagation effects. And then to do that, we need very accurate tomographic models that can accurately represent the effect of wave propagation at periods of interest. And here is the case of a joint work between our colleagues and people at different universities to generate a tomographic model for Middle East. And in this case, we have used the SpecHat M3D globe, which is again available through CIG. Another very important work that we're doing is actually come up with P&S wave speed global models that are used actually to locate earthquakes and explosions. And in order to do that, we need to improve our techniques, but also improve the knowledge about the underground structure. And this is a case where we have used let's see, so in this case, what we show here is the structure of the mantle and upper crust. For that model, we have used about 13,000 events, 7,000 stations, and we use about 3 million P and S wave travel times to get this very nice and detailed crustal structure. We use ray tracing and multi-popping technique to generate the structure. The model contains about 1.6 million nodes, and what's more important is that in comparison with the 1D model that we usually use to locate earthquakes, we get a 30 to 60% improvement in earthquake location. This is extremely important and significant. And again, I have here the link to where you can get some more information about the technique itself, but also to get the model. I'm moving really fast now. Of course, by getting a accurate travel time model, we could also try it and turn it into a velocity model and use SpecFM to see how well we do in comparison with other models to actually model high frequency or long period data. And here I just saw a comparison between how well we do with simulations using PREM, the G3D model, and S2029 EA model. And as you can see, this new model does slightly a better job, not only in terms of fitting the travel time, but also some of the amplitudes are better fit than the other models. Moving to earthquake ground motion in the San Francisco Bay Area. This is a very exciting work that we're trying to do. First of all, we want to know how well our numerical techniques can resolve the question that we have right now, that is, can the engineers actually use our simulations for their seismic design? So we're trying to come up with techniques that are easy to use, but also can be used by engineers, in the term that they can cover the whole frequency range that is used by engineers. Usually it's 1 to 20 hertz. So what you could do is, first of all, test the 3D model, as we did in this case, where we model the Loma Prieta earthquake in a period range of 1 to 10 seconds using the 3D model developed by USGS office. And we use that knowledge and that technique to actually understand how well we can do in actually predicting ground motion when we have a limited knowledge about the structure, topography, or the small scale structure. So in this case, we try to show the comparison between the recorded and simulated data using a original 1D model in the period range from 1 to 10 seconds. The next one is with a 3D model. Then we plug in the topography, which is also a feature that could be used in our modeling. And also we come up with a scheme to represent the stochastic characterization of the velocity, small-scale variability in the structure. And what we found is that including 3D and topography and stochastic characterization of the velocity models can improve actually our prediction, Gammon prediction. And now we're working hard to actually extend these simulations to much higher frequencies. And this is just a matter of maybe months or maybe next year that we'll try to have a full broadband simulation capability. And of course, this work is done in cooperation with SCAC, and we're using some of the technology that is already developed there to characterize the source and wave propagation. Another case, which is very recent, is we tested our simulation for the Napa earthquake. And here I show a comparison between simulated and recorded data. And our analysis of the 3D velocity model shows that the GS model works extremely well at period range from 1 to maybe from 0.1 to 1 hertz, but some of the simulations go up to 4 hertz, and we did get a really nice fit with the data. So we're trying to help also using our computation capability, help people to develop ideas how to use that in order to kind of improve our 3D models. And the last part of my talk is simulations that we're doing for several scenarios on faults in the Bay Area. Here I just show only one, which is the Hayward fault. The maximum frequency is 2 hertz. We're using a grid spacing of 25 meters, but we are trying also another run with a 10-meter grid spacing, which will push the Fmax at least at 3 to 4 hertz. And we start seeing a lot of wave propagation effects in the Bay Area. But we want to also focus our attention in the Delta area, where there is a lot of interest on the effect of earthquakes on levees or other infrastructures over there. And so we're making progress on that direction too. So I'm going to stop here, and I let my other two colleagues to continue, unless there is a very urgent question.
Yeah, while they're switching presentations here, if anybody has a question for Arben, please just chime on in or type it in the chat box. We'll, of course, have more questions, time for questions at the end as well.
Yeah, and also I want to say to other people that if they have questions, we can still communicate by email, or we're open to any discussion. It's not just only for this webinar. And I think the reason is just to share knowledge. And this is a lot of work, and it cannot be presented in 10 or 15 minutes. So let's keep it open. All right.
Hi, my name is Doug Dodge. So we're going to kind of switch gears a little bit here. Both myself and Stephen are going to be talking more about data-intensive computing than the traditional HPC. Stephen's going to be talking about the work he's doing to adapt commercial data-intensive processing architectures for seismological applications. I'm going to talk more about a use case we're developing for, which we currently think is one of our most interesting use cases for this sort of processing. Okay, thanks. So the motivation for this, one of our sort of principal customers, the USNDC, has seen their mission change over the years from being primarily teleseismic to now regional, and then moving to local scale monitoring. Meaning they're getting many more stations to process, and as they move down in magnitude, potentially orders of magnitude more events to process. And we believe that in time they're going to run into sort of a conflict between their relatively static workforce of analysts and their need to look at every event and make sure they're not missing something of interest. So our work in this field is to try to develop systems that use pattern matching to help them screen out from the large forest of events just those few novel ones that really need to be looked at by individuals. So to kind of lay the groundwork for the problem, here's a cartoon of conventional processing, and you can see that early on the incoming stream of data are parsed to produce a symbolic representation of the phase onsets. And from then on until you reach the point of analyst review, the processing is all done on the symbolic stream. It's a system that works well. It's worked well for decades, but it carries within it, if every event has to be reviewed, the potential for overwhelming the staff that have to review these events. It's been okay in the teleseismic and in the regional domain most of the time because the event rates are sufficiently low. But even with current systems, even with current systems, it's still possible to reach a point during intense aftershock sequences where the system's overwhelmed, partially because of the sheer numbers of events and partially because under those conditions of high seismicity rates, the system can make mistakes in association, which have to be undone by the analyst. So, we believe that there's enough repeat seismicity that if you could actually carry templates for every event you've ever seen and worked up before and use those to either actually cancel out or at least mask and identify the events you've seen before, that you'd be able to present the rest of the system with a much smaller universe of events to process and at least prolong the period of time during which the time until they run into real problems with processing, or perhaps solve that problem entirely. So what I'm going to cover in the rest of this talk is the work we're doing to establish whether in fact the signals are common enough to make this feasible, and then some work we've done to establish what the computational burden would be in implementing a system like this. So about 3 years ago, we really started working on this in earnest, and our first effort was a large-scale cross-correlation effort in which we used the LLNL GMP research waveform database we cross-correlated all the waveform segments in that to kind of understand what the global prevalence of correlated seismicity was. The map that I'm showing in this slide it's essentially the data set that we correlated, where the color of the seismic events indicates in that region what percent of the bulletin events we had waveforms for. So you can see it's a global data set, but not uniform in coverage. The sort of two interesting results relevant to my talk today are that globally, not very interesting 18% of events were found to be correlated, but more significantly at short distances, actually quite large fractions correlate, often more than 50%. The reason we think that's interesting is illustrated in this slide. What I'm showing here is the same global seismic data set, but color-coded according to the distance from the closest international monitoring system, primary or second or auxiliary station. And you can see that for the continental regions, virtually everything's within 10 degrees. And moreover, that's not a particularly dense network. There are a lot more stations out in the world than that now. The column in red in the table at the lower right-hand corner shows if our database were an operational system, the distances that we would have complete coverage in. And you can see that we're down to local distance ranges in terms of coverage. So to investigate how a detection processor would actually work using correlation over long time periods, we pulled into service a framework we'd already built for doing aftershock processing. This so-called dynamic correlation processor is a system which kind of bootstraps its way into building a comprehensive suite of correlators for a particular stream. You initiate the system with a power detector, and its detections are used to spawn new correlators, which can subsequently be promoted to subspace detectors if you wish. We've done a lot of work with screening techniques, including machine learning, to deal with the problems of invalid templates. I'm not going to talk about that anymore in this talk, other than my mention now that it's an important part of what you have to do to make this work. So we took a system like that, and our first experiment was to apply it to 5 years of data for the Central Asian Karatal array. And if you look at the top plot in this slide, what it's showing is the fraction of events detected by correlators versus the total number of detections as a function of time. This was computed in 10-day windows. And the kind of gratifying result you see here is that it's a generally increasing function, and at the end of 5 years, it's at or above 50%. So last December, we scaled this experiment up by adding nearly another 5 years of KCAR data, as well as 24 arrays from the International Monitoring System. So this is a much bigger problem, 50 times the KCAR data set in terms of volume, and also more than twice as long in terms of operating length. So we think it's pretty representative of what a real system would have to be able to process. Architecturally, it's primitive. We simply deployed our existing system on 9 independent nodes. We ran, each one was processing a single array. We ran it till the array was finished, started up a new one, and so on. But they got the job done for accumulating the data we wanted. This just shows the geographic distribution of the experiment. The color coding of the seismicity here is like with the International Monitoring System, but now it's relative to each of the arrays used in the system. The main point from this plot is you can see we do have pretty complete coverage in the northern hemisphere. We also have a few arrays in seismically quiet areas, so we've sampled more or less the range of continental seismicity you expect to have to process. And this is like a principal result from that study. Like the KCAR plot, the upper panel shows the fraction of events detected by correlators. I've broken it out here, though. The blue line shows all events, the fraction, and the green line shows events identified as being local signals based on the velocity as the signals impinging on the array. So what we see here is that at the end of the experiment, for all signals, we've reached a level of about 46% signals detected by correlation, about 56% for local signals, and there continues to be a linear increase in the slope of the detection curve, which leads one to hope that you'll continue to get improved performance over time. Quick point I want to make here is that it takes a lot of detectors to do this. I've arranged in this plot the detectors from most prolific to least prolific, and you can see even the first 10,000 detectors are accounting for only around 20% of the detections. It's the tens of thousands of detectors with only 2 or 3 detectors that actually make up the bulk of the detections. So you have to have those somehow in order to get these high rates of efficiency. Rate of detector production. So that's what I'm displaying here for each of the arrays. And the takeaway from this is, at the time scale of this experiment, the detector production rate's linear. Doesn't look like it's starting to curve over at all. So we could expect growth rates comparable to what we saw in this experiment, if this were put into operation. Some hope that you could prune detectors. This is showing the pattern lifetimes in green and the recurrence interval duration in blue. And you can see there are a large number of detectors that have both short recurrence intervals and short patterns lifetimes, which you might be able to prune, but you'd have to be careful in doing that. This plot shows for all detectors with a recurrence interval less than 20 days, the duration of those detectors over years. Obviously, what we're looking at here are mines. Some of these run for several years. These are important classes of detectors you wouldn't want to throw out prematurely. So we haven't worked out how you might prune the detector suites. Last thing on the sort of resources. This is the memory used by the system as a function of time. It's actually computed as though all the nodes were running simultaneously based on the resources within the code and the size data blocks and the templates that we were using. You can see by the end of the experiment, if all arrays had been processed simultaneously, we would have had just under 2 gigabytes of templates to correlate with the data, and it's growing at about 171 gigabytes per year, or basically a new processing node every year to keep up with the rate of increase in detectors. So this is a big data problem, not by virtue of the ingest rate, which as this slide shows is only 62 kilobytes per second, but because we need to have we're processing 200 gigabytes per second of templates, given our throughput and the size of the blocks of data that we're processing at a time. Oops, sorry. Here we go. Okay, so just the last couple notes on architecture. What I'm showing here is more or less what we did, and it's clearly non-optimum. The top node that I'm showing in yellow is maybe sized about right, but that's more or less by accident. The arrays that don't have much going on are not utilizing their resources fully, and some arrays just run out of resources and fail. And there were 4 arrays we couldn't process quite to the end of the data because we just didn't have enough RAM available. So we envisioned moving this system to some kind of in-memory data grid or Spark or perhaps some other solution. We're only beginning to grapple with that now. But whatever we do clearly has to be elastic so that you can easily add new resources as the system continues to operate and keep every resource fully utilized. So just to summarize this, we think that we're going to have to do something like this in the not too distant future in order to keep pipeline systems operating with their increasing loads. It's, we think, definitely true that a large enough fraction of signals repeat to make this kind of system feasible. And it's a big data problem. We're still looking for the solution to implement it. Thank you.
Hi, my name is Stephen Magana-Zook. I'm a computer scientist in the geophysical monitoring program, and my main tasks are big data analytics. Today I'm going to be talking about some of the big data tools that we've been exploring and applying to some recent data science projects. But the tools I'm going to be talking about today, most of them have entire books written about them or extensive online documentation. So this is going to be kind of a whirlwind tour. So these are the things I'm going to talk about. One of the major controversies of the lab is HPC versus big data. So I'll talk about first, and then I'll go and talk about traditional big data, which is Hadoop, some modern big data, which is Spark, and then talk about streaming and scalable databases. So what is big data? It's become kind of a hype. We'll use the term in a lot of different things. As an industry, it was a $30 billion industry in 2014. They project it's going to be greater than $70 billion in 2020. But at a practical level, it's just a set of tools and techniques for handling I/O-bound problems or data sets that have exceeded traditional database and traditional distributed computing capabilities. So HPC versus big data. At a high level, HPC handles CPU-bound problems where you have a small input compared to the output. So a traditional HPC might take a travel time model that's measured in megabytes and give you out gigabytes, terabytes, petabytes of simulation output, whereas big data is mainly focused on I/O-bound problems where you have terabytes or petabytes of input data, but your big data pipeline does a data reduction and gives you as output, really small megabyte or gigabyte files. As far as programming languages, at the lab at least, HPC is mostly Fortran or the C languages. Out in industry, you get more choices. On the big data side, the tools mainly support Java, Scala, and Python, although you could use pretty much any programming language if you don't mind the performance costs of it having a pipe out of process. For I/O, HPC has the compute nodes and the storage nodes, and the compute nodes have the inputs streamed to them, although at InfiniBand speeds. Whereas big data, the data is all local. So you push the computation, whether it be a Java jar or whatever the execution code is, you push that to the node that already has the data. So it's much less to send. Although typical big data clusters have 1 gig or 10 gig Ethernet, so it's a trade-off. Fault tolerance is handled differently between HPC and big data. HPC mostly does checkpointing, where the application state is persisted. Big data, whether it be Hadoop or Spark, goes to a slice or partition of the data, and if a node goes down, another node will just pick up that data through data replication and recompute whatever was lost. It's much finer grained. So when people talk about Hadoop, they could be using Hadoop as an umbrella term for a bunch of big data tools. But if you're talking about Hadoop proper, there's really two components. There's the Hadoop distributed file system, which is a way of storing the data that we're going to be processing. The input data that you put into HDFS is broken up into blocks, and each of these blocks are sent out to the different distributed compute nodes, usually through 3x replication. And what that gives you is fault tolerance. So if you lose a node, you don't lose your data. But it also gives you, or it gives the Hadoop scheduler flexibility in who's executing what task, because you have multiple nodes that all have the same data. The second component of Hadoop is MapReduce. And so MapReduce is a paradigm, but it's also an execution engine. And what it does is it looks at all of your input files, gives pieces of them to the same map code. You write a map function. You say, for each of these inputs, this is what I want you to produce as an output. The other part is the reduce phase. And a reducer is usually an aggregator. But since not all algorithms can be expressed as MapReduce, people kind of the paradigm to have reducers just output data or feed the results of one MapReduce phase to another one if you have like an iterative algorithm. And so MapReduce is more of a hammer that you apply to all of your data at once, and people really need screwdrivers. And so that's one of the things that we found as a con using Hadoop. On the plus side, when you use Hadoop, you don't have to really worry about any of the tedium that you do with distributed computing or HPC, whether it's message passing or the communication between the nodes. All that's handled by the Hadoop framework. Another nice thing is there's a tool called Hive. There's also another tool called Pig. But what Hive gives you is a SQL-based exploration of your data in HDFS. So instead of having a database, you're able to issue SQL commands against files. And of course, horizontal scaling. As your compute or storage needs increase, you're able to add new nodes to a Hadoop cluster or upgrade existing nodes. What a lot of companies are doing now are spinning up cloud clusters through things like Amazon Web Services. And so if you have a need for a 1,000 node cluster or a 100 node cluster, Amazon gives you the flexibility to choose whatever hardware specifications you want. Within 10 minutes, you have the cluster that you need. But there are obviously problems with Hadoop, which is why these new tools are being innovated. The first one, obviously, is not every algorithm is batch-oriented. There's iterative algorithms, there's machine learning algorithms that that need to update global state. MapReduce Java programming is verbose, and it's not intuitive, especially for data scientists who want to use Hadoop for data, real-time data analytics, which is why you see innovations like Hive and Pig, which add a higher layer on top of the Java. And MapReduce also has some serious I/O and network overhead. So MapReduce favors I/O. If you have a 3-step algorithm, in between each step, the results of the previous step will be written to redundant storage and then read back in for the next step to proceed. So one of the things that we've used it for is data exploration, which is one of the first steps you do as a data science project is you take in your data and then you look to see what you've brought in. We see things like quality control issues. We really expect our data set to have just a couple sample rates, the main ones. And what surprised us was we saw real low ones, less than 1 hertz. That was not expected. With Hadoop, a query like this, where you would do a group by, took us 5 hours to complete 14 node cluster. Hive is also good, I mentioned before. If you don't want to write Java, you can stay at a higher level SQL level. The traditional SQL has something called user-defined function. This is also present in big data. And what that is it's a piece of a Java function that you write that you want applied to all the incoming records. For this, a reduce becomes nothing but write this, write all the results to this. But to address the problems present in Hadoop, the AMP lab at UC Berkeley created this tool called Spark. What Spark introduced was 2 main innovations: the resilient distributed dataset, RDBs, and what RDBs are they try to leverage the distributed memory in a cluster, whereas Hadoop focuses on the distributed computation. And so when I was mentioning before about having to write all the results of intermediate steps to disk, Spark no longer has that. Spark has transformations on a distributed collection, and it will pipeline those transformations so that as you go from step 1 to step 2, all the data that you need resides in memory. So it makes for a really efficient execution pipeline. The other nice thing about Spark is it comes with a lot of valuable libraries that we were using Hadoop. You have to find from different open source projects. So like Spark SQL is a built-in library that replaces our need to use Hive. MLWig is a machine learning library that replaces our need to use Hadoop's Mahout. And Spark Streaming is a competitor, although different than a project called Storm, which I'll talk about later. And so with Hadoop, you really have two main transformations on data. You have map and reduce. With Spark, they also have map and reduce, but they add quite a few more. And so with a Spark RDB, you're either performing a transformation as you go from one step to another, or performing an action. The transformations don't actually invoke any execution. They're what's called lazy evaluation. And so the RDB will create a lineage of all the transformations that you want to perform. And then when an action is invoked, for instance, a count or a collect on that data, the transformations will be executed against all the incoming data. But that, as I mentioned before, those transformations will be done in memory, and the data will not go to disk between transformations. So how we use Spark in the context of seismology, the Spark SQL is also great for data exploration. We ingested 42 terabytes of waveform data and did the same queries that we did with Hive, except Spark can do it 2.5 or 2 times faster. It did all the queries in 2.5 hours. And this doesn't even take advantage of the things that the RDBs are supposed to help with, which is iterative algorithms and multiple steps. This is one step to do the full, what you consider a full table scan. And it's still did it 2 times faster, just due to the different ways that Spark is, the Spark infrastructure versus the Hadoop infrastructure in terms of network communications and such. But Spark is also good for the batch processing that we'd like to do, except we're no longer restricted to a MapReduce paradigm. This is an actual workflow that we have where you do a map with preprocessed data, a Cartesian of 2 different large data sets. Then you filtering another map to do signal extraction, and you finally release all the results into a manageable amount of files before you write it to disk. And so Spark's really the RDB abstraction opens the door to a lot of different workflows that would be difficult or just nowhere near ideal to do in MapReduce. As far as iterative algorithms, we will very soon be looking at the baseload code that Arben mentioned, which has a MCMC algorithm on 42 terabytes of ingested data. Another thing of interest is real-time streaming analytics. I mentioned the Storm project before, and what Storm introduces are two primitives, a spout which provides data, and a bolt which processes 2 bolts from a spout. And so you create these directed graphs that use as many bolts as you need in the processing pipeline, and you eventually you do things like update dashboards or write to disk. Spark Streaming is a little different. It also has incoming data streams, but what it does is it batches out input data. You could say wait for 1 second, wait for 500 milliseconds, but either way, it's going to collect data and then do these mini batch processings using the Spark engine. So you get all the power of Spark, all the transformations. You just do it on much smaller data. Okay. This one's okay. I'm confused. Maybe yeah. So what the slide that's not loading shows you is there's a project called HBase, which is a scalable database that runs on top of HDFS. And what it gives you is the capability of storing sparse data. So you can have what you consider a table in the database that has billions of rows, millions of columns, and not every column has to have the same number of values. And so this is the kind of the NoSQL, what people say the schema-less data stores. And so we looked at it in terms of storing time series data. One thing I didn't mention about HDFS is it does not like storing small files. And so we looked at HBase as a way of storing waveform segments in a way that did not upset HDFS. And by upset, I mean if you store too many small files, HDFS will just crash or run out of memory. What we found was for text and numeric data, such as seismic metadata, it's actually well, for your application it might not be fast enough, but for our cluster, you could write at almost 300 records a second. You could read at greater than 400 records a second, or you could bring in all the data. The full table scan is just giving everything, and that was 1,700 records a second. And so for non time series data, HBase seems to excel. But if you start storing binary data like time series, we ran into timeouts while we were trying to query data. And we also ran into the actual servers spending a lot of time doing Java garbage collection, which seriously degraded performance. So, and if you look online, it's not recommended to store binary data in HBase. And we found that to be true as well. So that was the whirlwind tour. If you try to incorporate any of these tools in your projects, there are many books and extensive online documentation for each one. What we found in general is that these big data tools are very promising for seismic research. It's just the challenge is you have to adapt it from being text-oriented into processing time series or blobs. With the rise of video and large image collections, the tools are already moving in that direction. Anyways, just natural evolution. Thank you.
Yeah, so if there is any question for all 3 or 4 of us, I would have some time to answer. If not, like I said, this is a teamwork, so we could take those questions offline and discuss about several aspects of that.
Yeah, thanks, Arben and Doug and Steve. I feel like we had this grand tour of seismology and a good introduction to a lot of the different activities that have been happening on the lab. Does anybody out there have any questions for any of our speakers today? As Arben mentioned, all our speakers can be contacted via email if you want to follow up on any of the topics today. There's a lot more detail behind what they presented and a lot of interesting work we're going to be very interested in hearing about as time goes on. So this seminar actually concludes our 2014-2015 webinar series. We want to say a big thanks to all of our speakers this year, everybody here for participating in the webinar series. This series will resume in October, so please check back at our website at geodynamics.org in the fall for our speaker lineup for 2015-2016. And everybody, thank you and have a wonderful summer. And thanks once again to Arben, Doug, and Steve.
Thank you, Lauren.